actually.
Okay.
So is it from your laptop or it is from YouTube?
From my laptop.
Okay. Just make sure with let me make sure with Hetu. He was going to share this on YouTube. Let me check.
Ankit, when you are ready, please tell me.
Yes, sir. It will take
So I can
1
just
or 2 minutes. 1 or 2 minutes, sir.
okay. Sir, am I audible, Arun sir?
Yeah.
Okay,
you are
okay.
audible.
Sir, am I audible, Arun sir? From here on, there is some issue, I think. Arun sir, in video, I think. Am I
Okay.
audible? Okay.
Yeah, you are audible.
Okay, but there is some issue in video, I think, is not able to run. So Ankit, are you there?
Yes, sir.
Okay, should I play? Just tell me when should I
सर एक्चुअली यूट्यूब में ट्रबल आ रहा है और लिंक अपडेट हो रही है.
okay. Okay, no.
हाँ हाँ ओके हाँ.
Sir, am I audible, Arun sir?
Yes, you are audible.
Okay, audible. Sir, am I audible, Arun sir?
Yeah.
Okay.
Audible.
Sir, am I audible, Arun sir?
Yeah.
Okay, audible. Sir, am I audible, Arun sir?
Yeah.
Okay,
You are
okay.
audible. रौनक मैं आपको कॉल बैक करता हूँ, एक वेबिनार में हूँ। हाँ, एक वेबिनार में हूँ, आफ्टरवर्ड्स मैं कॉल करता हूँ थोड़ी देर।
Sir, am I? Ankit, are you there?
Yes, sir. Yes, sir.
Uh,
Just a minute, sir.
okay, okay. Sir, am I audible, Arun sir?
Yes, yes, you are audible.
Okay, okay.
Rakesh,
Yes, yes. I can hear you,
have
sir.
transferred the video.
Mm-hmm.
Maybe I'll be able to uh, run that video.
Pardon, sir. Just come again.
Rakesh,
Yes.
I'll be able to share that video.
Okay, okay. So I'm stopping sharing
Yeah.
it. Okay.
Yeah.
So we can start video.
Yes, yes.
So we can start video.
Yes, yes. Sir, am I audible, Arun sir? Yeah. Okay, okay.
I hope I am audible to all. Hello.
Yes, sir, you are audible.
Yes, sir. Sir, can we start?
Yeah, yeah, you can start now.
Okay. So good morning, all the participants. So today's webinar, we have our expert, Mr. Arun Sankhat. Mr. Arun Sankhat is HOD of Design and
Okay, so good
Engineering
morning,
Department,
all
Post
the
Pension Service Private India Private Limited, Vadodara. Sir has done his graduation in Civil Engineering Department in Civil Engineering and thereafter completed his Masters from MS University, Vadodara. He served as a lecturer in Applied Mechanics and Structural Engineering Department, Faculty of Technology and Engineering, MS University, Vadodara, till 2006. He published research paper in technical journals and presented in international technical events. With the zeal to the something towards advance in construction industry, he joined Post Tension Service India Private Limited in 2006 and excelled in the design aspect of post tensioning technique. He is well versed with the concept of post tensioning and implemented the same in accordance with the Indian construction practices. He looks after R&D at PTSI and has performed tests in collaboration with IIT Madras for formulating design aspects of white slab system in context with Indian standards. So we welcome you, Arun sir. Sir, now we can start this session. So now it is hand over to you.
All right. Thank you, Ankit. Uh, let's start with the presentation. I think my screen is
Yes, sir.
viewed by all. Yeah, right. So it's related to the advanced system, which is prevailing in present building construction scenario in India. Actually, this system has been used since 1950s, late 1950s, or you can say early 1960s. So it's not that new to world, but maybe it is new to India. And since 2006, we are into this system. We are providing this system in India. So let's have a brief introduction and various aspect of having that unbounded post-tensioning system in building construction through this particular seminar. This is you can say this is an example or what we learn when we are into either structural mechanics or applied mechanics or stress analysis or any of the structural subjects in engineering. This could be the first example. We have a bending action, and for bending action we took a beam, simply supported beam, wherein there are two supports, a single beam resting on that two supports, and there is some weight on that particular beam, maybe as a central point load to start with, or UDL or UVL, anything. So here, as the beam is subjected to certain loads and certain supports, and with this boundary conditions, the beam is subjected to internal stresses, as we see here in this diagram. This diagram shows that the top part or top surface of the beam is under compression, and the bottom part, the bottom face, is under tension, or you can say maximum tension and maximum compression at top and bottom, and it varies linearly. And at certain point, like in this case, maybe at d by 2 or depth by 2, it is at 0, and then it changes the sign from compression to tension, or either way, vice versa. And actually we are familiar with this diagram. This diagram is nothing but a stress diagram, and we used to put this convention in the stress diagram, wherein C is kept as green in my case, and T, there is tension is kept at red, because concrete is good in compression. It holds good amount of compressive force or compressive strength. So that is why it is green for us. That is, it is good. We like that. The other way around is it is not so good in tension, in handling tension. So that is why that is a red signal for us, and we need to take care of that part, or that weakness of the concrete. So generally what we do is we provide uh, a element or material which is good in tension. So in short, we are providing steel or metal part material to take care of the tension portion. So that is a basics of RCC or reinforced concrete design. Let's go beyond the RCC, and further on to that, if we go, that is the pre-stressing. So just to have a brief of pre-stressing is nothing but whatever the internal forces that is expected in the beam, we are trying to generate a reverse kind of internal actions into that particular member before it is under service condition. So that is what is the meaning of pre-stressing. So we are trying to stress the member in such a way that it will produce, or it will generate the internal actions in such a way that it can resist or it can nullify the internal actions which are subjected when it is under service condition. Again, the same example with improved, or you can say further advancement in the conceptualization. So here you can see that the same beam, right? And what we are seeing over here is there is a blue line. So that blue line is nothing but it is a cable, or you can say pre-stressing cable or pre-stressing wire. And let's understand that part. So let us understand first this part. This is nothing but it is known as pre-compression. So in pre-compression, what is happening is, let us understand with this example that you have a stack of book like this. So there is a bottom platform, and on that bottom platform, the certain books are resting on. And if we remove, or if we just remove the bottom platform, what will happen is book will not be under equilibrium condition, and that will fall down, right? So other option to get the book in the place is to generate a pre-compression in both the directions of the book stack, such that there is the internal cohesion between the surfaces of the book, and it holds its position, right? So that is the meaning of pre-compression, or you can say concept of the pre-compression. So you are getting a benefit of having pre-compression in your member in this direction, right? So that is one part. Actually, this concept has been materialized or thought by Professor Magnan, uh, and that was the initial first step of pre-stressing. The second step of pre-stressing, or you can say further advancement in the conceptualization of pre-stressing, was being developed by Professor Lin, T.Y. Lin, and he developed the load balancing concept with the same cable. If the cable is straight, we are getting pre-compression. If the cable is having certain profile like this, what you see here. So if you have a certain profile like this in cable, what happens is you are getting additional benefits. When the cable is stressed from both the ends, what happens is cable will try to straighten up, and it will start uh, inducing the force in this direction. And again, there is a beauty of that force, that it helps us in resisting the gravity forces. So gravity forces are acting downwards always. and this force, the part force of that is acting upward, so that can balance the gravity forces coming on the beam, and that is how it is helping us to reduce that the net effect. And again, it has a benefits of reducing the stresses as well as deflection in the beam. So now altogether, let's see the altogether entire scenario. What is happening is, we are getting this P over A, that is pre-compression through this action. We are getting this kind of internal actions through this P by this weight balancing action. What is happening is, ultimately here what is happening is, you can get you can see that these are the pre-compression forces. You can see the green arrow is the pre-compression forces. The black upward force is nothing but the weight balancing forces. So altogether, if we sum up, this is the design stress, what we get from the loads, or you can say vertical downward loads on the beam, that is moment divided by sectional property, that is Z, or you can say section modulus, wherein you have a tension at the bottom and compression at the top at mid span of the beam, and the additional action you are getting from pre-stressing is pre-compression, like this is the direct stress. So direct stress is nothing but pre-compression force divided by the cross section area A, plus you are getting the load balancing or weight balancing force or stresses, that is nothing but the pre-stressing force into the eccentricity, and divided by the sectional property Z, right? So in nutshell, or you can say, altogether, if we sum up the internal actions, the final stress diagram could be like this, wherein you'll have more of C and less of T. Now here you can have a control over T and C both, or tension and compression forces or stresses in the beam. Here you can make this T or tension force 0. You can have entire section under compression. You can limit this T to your codal provisions and whatever is acceptable by code. You can control the amount of tension accordingly. So the beauty over here is, uh, you can actually control the stresses, or to be more specifically tensile stresses. And what happens is, if we can reduce these tensile stresses, you can reduce the cracks, because tension in the concrete is bound to crack if it is more than the certain values. So there is a tensile strength of the concrete. As if we go with the M30 grade of concrete, the compressive strength of the concrete is 30 Newton per mm square, whereas the same concrete bears tensile strength hardly 1/10 of that. That is around 3 Newton per mm square. So compressive strength is 30. Hello. So compressive strength is 30, but its tensile strength is hardly 3 Newton per mm square. Right. So if your concrete is having stress more than 3 Newton per mm square, in that case, it is bound to crack. And once it is bound to crack, and if the crack width is more than the permissible, the crack can reach to the reinforcement, and if it is reaching to reinforcement will be exposed to the atmosphere, and it is bound to have corrosion if the environment or surrounding is highly corrosive, or it may be having a chemical gases nearby which are corrosive, then it is bound to have a corrosion in the reinforcement, right? So here you can have that, like in case of water retaining structure, maybe you can have this diagram all compression or having zero tension in any of the phases. You can have a control over that, like this. So in building construction, actually this tension part is allowable based on the codal requirement, so that we can economize the structure, we can have a better optimization over economy of the structure. Now here, as I mentioned, the eccentricity, right? So somewhere I have mentioned the eccentricity P over E. So here, if you see, there is a part of eccentricity. So P into E by Z. So what is eccentricity? Let us understand the eccentricity part. Uh, to realize the influence or effect of eccentricity, let us have this example or this example of this bridge. This bridge is very well known bridge. It is the Golden Gate Bridge in San Francisco in California, USA. Uh, Many of us, or being an engineer, you must have uh, uh, seen this bridge, the other view of the same bridge. Now you must be able to identify that bridge, right? So we'll go through this bridge. We'll study some of the aspect of this bridge. So here the bridge has two piers or pylons, two supports. You can see one is here, another is here, and the span between these two support, the clear span is around 1.28 kilometer or 1.3 kilometer roughly. Now here, to achieve this unsupported span 1.3 kilometer, they had to go with a height of this pylon around 230 meter from the mean sea level. So why to go with this much height of pylon? That is a question, right? So actually they wanted to achieve this eccentricity of 150 meter. That was a case, right? So to achieve this 150 eccentricity of this cable, that is required, or that is the optimized eccentricity. And to achieve that, they have to go with 230 meter of the height of the pylon. Now, what is that? So height of eccentricity only is can be realized with the height of 50-story building. So eccentricity is 150 meter. If you consider 3 meter per story, it is around 50-story building, just the eccentricity. And if you think of 230 meter, the height of pylon, it is more than that, maybe around 75-story building, right? So why to go with that 75-story building height of pylon just to achieve this 150 meter eccentricity? So this is the you can say essence of this bridge, to have this eccentricity. And why this eccentricity? Let's study more on that. So I'm keeping the same eccentricity or same cable, and I'm turning out now towards building applications of the same concept. So now you have a beam, same kind of structure, you can say. It's not same kind of structure, but same analogy, you can say. And here now the same kind of eccentricity or same kind of curvature or profile of the cable is generated in the beam. You have two span, you have a particular span and two supports here and here, and maybe you have a continuity, right? So now you have this kind of cable profile, and now you know that what is the extent or why the eccentricity is required. So in case of bridge, we went up to 150 meter height of eccentricity. Now the same is not the case in case of building, right? Say this is a beam or slab. Now client or we want this eccentricity, or ultimately the total depth of the member to be as minimal as possible, right? So if you want to make this as minimal as possible, what happens is we are getting less eccentricity. And if we are getting less eccentricity, what happens, or what we need to extend, or what are the limitation in that case? Let's study that part. So here the same kind of experiment, or you can say a simple experiment, we may have this tool or setup in our laboratory, wherein we have a blue color cable, elastic cable, or you can say it's not elastic, but it's a flexible cable. And with that cable, there is a pulley here, and you are tying some weight to that cable, right? And then you are having some weight at the end of the pull this string. So to balance this, to make this system under equilibrium, with this kind of uh, load, or you can say force in the cable, and with this kind of force or weight on the cable, there is a certain amount of eccentricity that is being set with this to make it under equilibrium. Right. Now, what if we need to reduce this eccentricity? The only way to reduce this eccentricity, because we have a fixed amount of weight. So to reduce this eccentricity, what we need to do is we need to add on some more force over here. And if we can have some more force over here, then and then the eccentricity can be reduced. So let's see that. So this is the second case wherein we can reduce the eccentricity by providing more force in the cable, right? So actually, what is happening is here uh, we need more force in the cable, or maybe we need more cables to reduce this eccentricity and to minimize the overall depth of the beam or slab. So that is where the eccentricity plays a role. So higher the eccentricity, higher is the load balancing force generated by a cable, and lesser is the force required in the cable. Whereas if lower is the requirement of eccentricity, lower can be the load balancing force, and to make it higher, the force in the cable must be higher. That is how the equation should be. So now you have the clear picture about all the aspect of the system or prestressing system. Now there are two kind of prestressing systems. One is known as pre-tensioning systems, which is nothing but you are stressing the cable, or you are applying the force in the cable before concrete is cast. That is what is meaning of pre-tensioning. You are tensioning the cable before concrete is cast. The second one is post-tensioning system, wherein you are stressing or you are pulling the cable, or you are applying the force in the cable after concrete has reached its desired strength. So after having cast of concrete is poured, and maybe we need to wait for certain days, and after certain days, when the concrete has reached to its desired strength, so that we can stress the cable, then we are stressing the cable, and you can say the force is applied to the cable after casting. So this is a basic difference between pre-tensioning and post-tensioning. Pre-tensioning has its own limitations of dimension of the elements. It is generally used in short size elements, and generally it is used in controlled environment where you have a high strength, high force resisting system is there, because you don't have concrete to resist the force, and that force, when you apply, when the concrete is not there, that must be resisted by some other system. So it needs that strong system to resist that force, and that may not be feasible to achieve on site. So that is why it is generally a factory made or controlled base, or at certain place only the manufacturing of pre-tensioning elements are being carried out. But that is not the case in case of post-tensioning system. Post-tensioning has its own advantages, like it can be cast on site, and it can be used in situ projects. In post-tensioning, you have a grouted PT system. The other name of grouted PT system is bonded PT system. You must have seen in bridges. The second one is unbonded PT system. or you can say, to be more specifically, it is mono-strand PT system, and it is generally being used in buildings. And now, it is started also, it's used in bridges in Germany and other European countries, and as well as Japan and Korea. So we are dealing with unbonded PT system, and we'll discuss about that in the forthcoming slides. This is how it looks like. This is the icon of unbonded PT system, wherein uh, this image specifies actually a side of a slab, wherein you have a anchor block nailed with the side, wooden side, and blue color cable is passing through that, right? And here actually, either you can say it is a limitation. The only limitation over here is quality of concrete. If you are having a controlled quality of concrete, you will get better results or better performance of having this system in your structure. These are the nuts and bolts of the unbonded PT system. There is a PT cable, there is an anchor plate, there is a pocket former and wedges. So this all will sum up the anchorage system, and this PT cable runs throughout the member, either it is a beam or slab. Uh, this is known as standard system, whereas there is a other enhanced system which is known as encapsulated PT system, wherein everything, this metal part is also uh, covered with the plastic polyethylene or polypropylene plastic sheathing, or you can say encapsulated throughout. So everything, nothing, no metal part is exposed, and everything is covered with the plastic sheathing or plastic cover. It is known as encapsulated PT system. Below is the structure of cable. To be more precisely, you can say the cross section view is like this, wherein there are 7 wires, which is made from the high tension steel grade, and there is a grease coating on that. This grease has two properties predominantly. One of them is to protect the cable from corrosion, so it is a corrosive resistance grease, or you can say anti-corrosive grease, and it has it allows the sliding of the cable while stressing. So it allows the stressing, and it reduces the friction actually, while stressing. So it performs two, like it protects the cable, as well as it provides less friction to the cable while stressing. On that, you have it has a HDP sheathing. So sheathing also has two purpose. One is, the main purpose is, you can say, to protect the cable. The second purpose is to make it unbonded. Right? It's the cable is not directly in contact with concrete. So to achieve that, this HDP sheathing helps us. You can go through this later stage, because this is all cost to benefit ratios. Maybe that part is self-explanatory. Once you have a lesser thickness members, your self weight is reduced. So overall, from foundation, columns, at every level, you can have a benefit uh, of having less consumption of steel as well as concrete. You can achieve more span to depth ratio. Secondly, if you are achieving maybe 1 feet at every level, maybe on 11th or 12th floor, you have additional floor, so of the same building height. So that is a part of builder. Actually, builder will like if we can add on 1 story extra in the same building height. He will love that. uh, we can have a better control over the stresses and deflection. So ultimately, you will have a higher durability performance on your building, overall building. Let's discuss about brief history of post tensioning. In 1986, the first patent was being issued to PH Junction of San Francisco. So it's in 1886. Then in 1928, Prestressing has tried to play with this concept, and he used high strength wire and concrete and start using this in France. Then in 39, the same guy has again improved that. He tried with the conical wedges and special jacks, and he has developed something to anchor the wires in 1939. Then there was a red dot in the history. There was a World War II, and in World War II, there was a vestige of steel infrastructure. Everything was washed away, even building roads, bridges. So after having this World War II, the post-World War scenario was such that there was a huge demand of again constructing the infrastructures, buildings, roads, everything, and the metal part was being wasted in carrying out the World War II. So again there was a scarcity of material, and there was a huge demand of making all these structures. So again the post tensioning came in picture, because it was actually saving the material. To progress on that, for in 1949 50s, the first practical use of PT was in one of the bridges in Philadelphia. The bridge was Walnut Land Bridge, and in 52, the same system has been in use in or applications in building sector to make a cold storage warehouse in Philadelphia, in Colorado. Sorry. In 1960s, it has been in use for the nuclear containment structure. In 1970s, there was a development in metallurgical side, metallurgical engineering side, in casting, and again that has helped us to making efficient anchorage system by casting. In 1976, there was a formation of PTI in USA, and this PTI Post Tensioning Institute is you can say a regulatory body to furnish, to make criteria, standards, specifications related to post tension. So we are following this PTI body in our system, furnish. Uh, these are some of the state-of-art developments. Many of them I have already discussed. One of them is that specifications are made for unbounded PT system. So it is a well-specified system, you can say, in other words. The second one is system of extruding plastic sheathing. Whatever the structure of cable you see right now, this is nothing but the same. You can say the extrusion of plastic sheathing around the grease strand was developed. So this kind of system was developed to have this kind of extrusion system. Then the ductile iron casting in metallurgical side has been developed, and that has helped us in preparing efficient anchoring system. Then concept of weight balancing, we'll see this in one of the slides, in forthcoming slides. Banded and uniform, this is also we'll see in some of the slides. Then computers have come, and it has excelled our analysis and design compatibility capability, as well as the efficiency, so the speed actually. And then finally the encapsulated Pt system, what we've seen to work against the corrosion. So this is how it looks like. This is a typical or schematic layout of unbonded Pt system, wherein a part of that is already this is already cast with the Pt system, and there is a construction joint here. So after that construction joint, this part is yet to cast. The laying of PT is already done. Some steel is also there, right? And this cable is coming out from already cast portion. This cable is also coming out from the already cast portion. There are cables in the cast portion like this. So now, after having sufficient strength of the cast concrete, we are preparing it for stressing. Like we are removing the pocket former, applying the wedges, and then we are applying forces through this stressing jack, and we are pulling them out with certain amount of elongation, certain amount of force, and then they are self-locked with the wedges once the force is removed. So inside there is a force in the cable, and then after having this stress cable, we are cutting this excess length of the cable, and everything is flushed in. Nothing is taken out of the face of the uh, slab. These are the real photographs of the system. Uh, if you see this, this is a side of the slab or beam. This is a pocket former. This is the anchorages, and the cable is taken out. So this portion is for the stressing part. Once the stressing is done, this portion will be cut. You can see the yellow part in this. This yellow part is nothing but the grease. Right? This is from inside view. You can see these are the cables. The group of cables are separated out at the anchorages, and then every cable is treated individually. That is why it is known as monostrand system. So each cable has its own anchorage system associated with the single unit. So that is why it is known as monostrand system. Uh, these are some of the you can say some typical layout of the cables. Some cables are going in X direction. Some cables are going in the other direction, orthogonal direction. And you can see the cables are being laid with certain profile, like high point, low point, and gradual transition between them as per the design requirement. And this is the final outcome. These are the pockets, you can say. Once the stressing is done, the cable is cut, so it looks like this. And then finally, that patch work is done, so that everything is hidden inside. You will not be able to identify whether it is PT or normal RCC from the exterior perimeter, because it is all sealed inside. Let's see some of the applications in residential projects. Yeah. So here, in this scheme, actually, this is a flat plate scheme wherein uh, you may be able to see the perimeter of the slab, and whatever green part you see, these are the supports. So these are the supports. You can see these are the supports. Here also, there are supports. Like these are the supports. So green part is nothing but these are the columns or shear walls, or you can say structural walls. So here actually there are very few beams. Maybe there is a beam here, there is a beam here, like that. So the beams are actually placed in such a way that they are not hindering the ambience, or you can say the space or working space. There is no beam inside this portion, you can say. So it's only flat scheme, and you can see the laying of the cables are being laid in you can say distributed and bent uh, scheme. So horizontal cables are being laid in a group, and vertical cables are being laid in distributed direction, in distributed way, with uniform spacing or something like that. So this is a uniform and distributed cable. Uh, you can see the photograph of the same project, wherein a flat scheme is there, and some of the cables are being laid in distributed direction, like uniform sorry, banded direction, and in other word, in other direction, like this. These are the distributed uh, spacing spaced cable laying. So here you may observe that the cables are at high point here. These are at high point and then again low point here, right? So this is a high point, again low point, like that. High point, low point, like that. High point, like this. And this cable also high point here and low point here. So these are the cable profiles required as per the site, as per the design requirement, and this helps us in inducing the weight balancing as well as the pre-compression from both the ends. This is the project wherein the floor to floor height was 10 feet, and you can see that the support and slab directly. There is no beam. The other is flat slab with column drop panel. This is the another scheme wherein this may be in commercial or this can be used in residential as well. As you see here, there are drop panels like this. So these are the drop panels. These are the surrounding the column, and there are few beams. Maybe here. These are the some beams. So the beams are as per requirement of the structural consultant. We are working with the structural consultant. We only actually concentrate our design to the post tensioning part, and other part is taken care by the structural consultant, like columns and beams, maybe RC beams or shear walls and footing and all these things will be designed by the structural consultant, and horizontal members, PT members like beams and slabs will be designed by us, like that. So here uh, uh, the span could be like 10 meter or 12 meter or 11 meter from column to column. So to achieve that span, in RC case, the deflection will govern the design, and you must have the thickness so that the deflection is taken care in case of RC. But here in case of PT, you have a benefit to control the deflection. That is why you can reduce the depth of the slab and depth of the overall floor plate. So this is the image of the same drop panel and column flat slab scheme, wherein you can see these are the columns, and this is the thickened portion. So this is the drop panel. Here also there is a drop panel, thickened portion. You must have seen some cables are starting from this inside middle way of the slab, and many of the cables are through slab edge to slab edge. So this is as per the design actually. When if you have a larger span here and if you have a lesser span here in this portion, you may require more cables in the larger span. So we may put like this. This is once the casting is done, stressing is done, and when the shuttering is removed, this could be the scenario or the ceiling of the PT slab. This is known as flat slab with drop panel. You can now easily view the drop panels around the column. The other one is flat plate in the commercial part. This is a commercial project wherein flat plate is suggested. You can see that there is no drop panel or thickened portion in the column and slab junction, but there are few beams, you can say. So beam geometry is here, beam is here, beams are here at the perimeter. So in working part actually there are no obstruction of the beam, so it is easier for the services to pass through from the ceiling part. This is another project or another scheme wherein client wanted to save on the height of the building, and actually we proposed this kind of scheme wherein this was a larger span. So in larger span we tried with this kind of PT beams. These are nothing but the flat or wide shallow beams. If the section will be like this. This is the slab thickness, and this is the thickness of this wide shallow beam, and it moves like this in 3 dimensions. So it has you can say width is more than the depth of the beam. That is the wide shallow beam. So with this scheme, a client has saved on the height of the building. And this particular plan is nothing but it is a plan of old Linde building in Vadodara. It's nearby Buda Circle, near Kareli Bagh, LNT Circle. There is a building. So this is the planning of that particular. It was actually rented by Linde, and now Linde has its own new building. So they are shifting. They have shifted to the new building, and that new building is also our project. I'll show you the slides of that building also. This is another project wherein client was having columns here. There were columns here, and client approached us that I want to actually have a better working space in this portion, but he did not have any issue with the height of the building and height of the beam actually. So what we tried is we tried with the same height of the beam what he was having with the RC and with these columns, with these central columns. In RCC he was having certain height of the beam. So with keeping that particular height of the beam, what we tried is we tried to remove this entire row of the column with the same height, and client appreciated that, and then we moved forward, and this project was materialized. So now you can see the beauty that there is no column inside the building. It's all it is the freedom of client that he can make anything in this unobstructed area. This is another scheme wherein ribbed beam with slab was proposed, and this is a peculiar, or you can say a typical scheme for the industrial projects, industrial sheds, wherein actually they have a requirement of larger span in this direction. You may have lesser span in this direction. They don't mind. So these columns are spaced accordingly, right? So this span was around 20 meter. This span was around 16 meter. Here this span was around 12 meter, and this span was around, I think maybe around 8 to 9 meter. And they wanted to have lesser depth beam in this direction, in this direction. So they have went with the ribbed beam. Also, the loading was very huge on this particular floor. Actually, this is a building. This was a building for Volvo Eicher vehicles, to manufacture those vehicles, bus and automotive vehicles. They wanted to have this kind of roof, or this kind of floor. Sorry, the roof is of steel structure. It is very lighter. That is above this, but they wanted to have this floor so that they can utilize this floor for manufacturing of those ancillaries and truck. So this is a photograph of the same scheme. You can see that here this floor, this particular floor is a PT floor with a certain depth of the beams. This is a maybe a 12 meter. Inside there is a 20 meter, and then 16 meter, like that. You can see the side view of the same. This is a floor wherein heavy load is expected to come, and then there is a roof above that. That is a lighter weight structure. There was actually only the self weight and other wind and seismic forces coming on that, no other load. This is a very interesting geometry known as waffle slab, wherein you can see this. These are the columns. So there are total 8 columns. There is no inside column. It is all columnless space. This span between this column from inside to inside, or from center to center, is around 124 feet, and here it is 120 feet. So it is 120 feet by 124 feet. Spanning was there. And these are the cutouts inside the floor, or you can say roof of this building. Actually, this is a very special structure, and this structure is already constructed, and it was actually, it is the largest flat roof in the world, and awarded by Guinness World, and it has that record, Guinness World Record, of having largest flat roof in the world. And this is in Jaipur. It's just adjacent to the Govind Dev Ji temple, which that is a well renowned temple in the Jaipur, just nearby the Hawa Mahal. It's just beside that. There is a Raj Mahal of the king of the Jaipur, and it was managed by the king, and now it is managed by the government of Rajasthan. They wanted to have this kind of satsang hall just nearby the temple, and the restriction was overall height of the building. So they wanted to keep the overall height of this building that lesser than the height of the temple, and with this span. So they were not able to manage with the RC or RCC. So then they approached us, and we proposed them this geometry, and it worked out, and then it went well. So this is the image of the same structure. Now you can see that there are only 8 columns. Whatever you see are the architectural effects only. This is the real column. This is the real column. This is the real column. These are not the real columns. These are just architectural aesthetic members. So it is completed in 2009. The loading above this is like, it has a 500 kg per meter square load is with which it is designed, so that even the gathering above this floor is it can be allowed. So it is designed accordingly. Let's see some of the technical part. One of them is serviceability. What is the meaning of serviceability when as a designer perspective? So these are the points, these are the aspects we need to look after while designing the PT member or any RC or any member. So one is the deformation or deflection. It should not be beyond the limit permitted to by the code. Cracking as well, there is a limit, so it should be limited with that cracking part. If this cracking is limited, then again durability can be managed by reducing the cracking. The other part, like impermeability, vibration, acoustics, thermal insulation, these are secondary part, but these are being taken care by some other agencies. So actually the serviceability is expected to remain effective throughout the life of the structure, because the structure should be serviceable enough so that it can be uh, made use, right? So to have this structure serviceability criteria should be messed up while design. The other part is strength. As a designer perspective, once the serviceability is confined or made sure, maybe we can go with the strength aspect later on. So in strength, its occurrence is very rare. So actually the serviceability or strength aspect achieves or arrives at the last stage of the member when it is about to fail. Serviceability parameter exceeds the limiting range. Now in strength aspect, it is expected that now the structure is not serviceable. It should deform excessively. It should show the cracks. It should show the extensive deformation, noticeable deformation, so that uh, we can foresee, or we can notice that it is about to fail, so that we can save the human life. So both are contradictory actually. Actually, in case of serviceability, we don't want structure to get deformed. We don't want any cracks in the serviceability criteria. But in case of strength, we want that structure should crack. It should show in enough amount of deformation. It should deflect before it fails. Right. So we need to design for the both these extremities. So in case of strength aspect, we need to ensure that the failure should not be sudden. It shouldn't be a brittle failure. So there has to be enough level of ductility in the structure in the member so that it shows the signs before it fails. So let us understand that how to achieve that strength and ductility both. So here, if we see the material characteristics, the characterization of the material, we are using HYSD steel. Initially, we were using mild steel. You can see here the mild steel graph of mild steel, that is stress versus stress strain diagram of the mild steel. It is well known to us. One step ahead is the HYSD steel. We are working right now with the HYSD steel, which is having a more strength than the mild steel. Right? So now we are having working with the Fe500 steel, that is here, and beyond, one step ahead, you can say, is the pre-stressing steel. So we are jumping from this to somewhere here, 1860, right? So we are gaining much as far as its strength is concerned, but we are losing something like this as far as its strain is concerned. So here, the strain aspect is this much only. So strain has a relationship with the ductility. If you're reinforcing steel having more strain while failing, it will add up a ductility to overall structural behavior. So here, actually, we are losing the strain aspect or ductility aspect while using the high strength material. So as you know here, uh, let's compare both the things. One is uh, uh, stress versus strain diagram of PT. So this is a PT cable material stress strain diagram, and this is the normal reinforcing steel HYSD or maybe 415 steel grade stress and strain diagram. So here, the peculiar thing is, this strain when it fails is hardly 0.06. So it fails here, but the our steel goes up to maybe double of that, 0.12. So here we need to make sure about that, and we need to take care this part in our design. So how to take care of that, and what is the actually resultant or effect of this kind of strain characteristics in the overall scenario? So these are the graphs, or you can say combined graph of PT as well as steel, normal steel. Let's understand this part. So here what is happening is, if it is a bonded PT system, then prestressed tendon is bonded with the concrete, as well as reinforcing bar is also bonded with the concrete, and both will be at almost at the same level, which will be nearby the tension phase, right? So what happens is, in case of strain compatibility, everything having same strain level at a certain level of stress, right? So or certain level of your depth of the member. So in mid span of the beam at bottom, maybe the cable and reinforcing steel as well as concrete will have same strain level. They will have different stress level but same strain level, right? That is the meaning of strain compatibility. So what happens when the strain compatibility is there? So when the strain is increased to such an extent that the strain at which the bonded PT cable fails, so there is a sudden change in the transfer of force, and now the force is experienced to the reinforcing bars is more, and there can be a sudden failure of the structure. This case is expected in case of grouted PT system. And in case of unbounded PT system, what is happening is, the beauty of making it unbounded is like, whatever you have seen in the last slide, this is the same thing here. So this is the stress strain diagram of bonded PT system, wherein this is failing here. In this portion, it fails. But in case of unbounded PT system, what happens is, let's see that it goes further, and it fails. It is about to fail at this point. And if you see that, the strength part, it is very, very high, as well as the deformation part. Again, the deformation part, this, and deformation part here. So this actually, this behavior is known as catenary action. You can search on the Google regarding this catenary actions of unbounded PT system, and you'll get to know that, how beautifully it can help us in achieving the ductility, as well as in achieving the greater amount of strength. So ductility part in unbounded is what we saw right now. But in general scenario, the ductility can be managed by confining the concrete. So here, as you see, this graph stress versus strain, this shows that, the graph of stress versus strain of unconfined concrete. So you just watch out the strain part. Strain part is this much when the concrete is unconfined. But when the concrete is confined, so this is the graph. It improves a lot in as far as its strength is concerned, and as far as its uh, strain or ductility is concerned. You can see that, it is enhanced by just by confining the concrete. So confinement can be with the help of this longitudinal steel, and more of with the help of this kind of transverse steel, that is nothing but the stirrups. So by having the stirrups, by making the beam having a good amount of stirrups, well specified in accordance with the ductility code, that is 13920, IS 13920 is the code to achieve good amount of ductility that is required to take care of the lateral forces. So that can be managed with the help of this kind of steels. Earthquake and unbounded PT system. Let's see a scenario wherein, you have a portal frame, you have larger span, and you have columns at the both ends, and you have a UDL like this. So this is a gravity forces, and with the help of gravity forces, your member will be subjected to this kind of bending moment diagram, wherein, negative portion is the hogging, positive portion is the sagging, and again negative portion. Let's have earthquake force or lateral force in one of the sides. So it will generate this kind of bending moment diagram, where, at the one of the end you will have a sagging, and the other end you will have a hogging, right? And at the midspan you will have zero moment, you can say, ideally. Let's see from other end, like reversal case, the sway from the other end. So this kind of envelope moment will be generated in case of lateral forces, right? And if you can watch out the middle part is still unaffected. There is no moment in the middle part. Only the moments are generated at the column beam junction. Now let us think all together. Let us superimpose everything. So I'm superimposing the things. So now this is the scenario, right? So this two thick black lines is nothing but the envelope part of the moments, wherein, midspan portion is controlled by the gravity moments, whereas uh, near column beam junction the portion is partly there is a gravity moment as well as the lateral moments. So here, this way, we can take care of this part with the post tensioning. Here there is also post tensioning, as well as, maybe we need to put some extra steel on top and bottom of the beam. element. And with this, we can design the lateral forces as well with PT. This is regarding you can say stiffness to be considered for the RC members in case of earthquake. When the earthquake is there, with the earthquake, in earthquake analysis, we need to think of the I gross, or you can say the moment of inertia, gross moment of inertia, as well as the effective moment of inertia. So code says, the IS 1893 code says that 70% of I gross in case of column, as well as 35% of I gross in case of beams. So hardly you are getting any stiffness of a beam member, because it is just 0.35 times, and this will lead to a higher design or higher depth of the member, right? If we want to design with this, and in RC members, in beams, only 35% you can consider, and this will lead it to higher depth of the member. Still, this 1893 is not upgraded, and it has not included the PT part, the effect of PT, but certain other codes like ASC has introduced that. This is the table 10.5 from the ASC 4117, the latest code. You can see that beam non-pre-stress, it is almost same. In our case, it is 35%. So here it is 0.3, 30%. The flexural I gross they can consider. But in case of pre-stress beam, you can consider 100%. It is 1 time I gross. So that is the beauty of, or you can say, the advantages they have considered in case of PT system. So here you can have lesser depth. This is because you can have a better stress control. And why this is 0.3 in case of beams, non-pre-stress beams, is because of cracking. It exceeds the tensile stresses, and that is why there is a cracking, and that is why the cross section area available is less, and that is why they consider 0.3 or 0.35 of I gross. Whereas in case of pre-stress beam, if you are able to control the stresses, if you are able to minimize the tensile stresses, you can reach to this, and you can have the benefit of that in this case. Practical aspects of the PT system. Now let's switch over to the practical aspects. Some of the photographs from the site itself. This is the installation of large size PT beam. Here the side faces are open, and the installation is carried out so that we can ensure that a proper curvature or proper profile of the beam cable is generated inside. And then before casting, the sides are put on place, and then the casting is carried out. The span could be like 50 feet from column center to column center, and it is a single span beam. This is the installation of extra large size PT beam. You can compare the height of the beam with this person, right? So it's more than the height of the person. Also, you can see the cable profiles. These are the profiling of the cable. Actually, this project was in Baroda, and this is of Nilambar, one of the projects of Nilambar. It's nearby Vasna Bailey Highway, Nilambar Circle. There is a Hyatt Palace Hotel. This is a project of Nilambar Triumph, wherein they had a transfer of structural systems from one of the floors above the ground floor, maybe around 6th or 7th floor. They wanted to have a different structural stream above this particular level. So this is a transfer level, whereas this is the transfer beam, wherein there are certain columns coming on this particular beam, and they are not going below this beam, right? So this is transferring the force from those floating columns to the main columns from this particular floor. You can see the end of that particular beam. the series of anchor plates are being arranged with a particular profile. This is the same beam after having cast, after having stressed, and the cables are cut, and now it is about to fill the recess or this black pockets. And once it is done, everything is over, and you can move forward. So this is how it look like afterwards. Some other interesting cases of post tensioning. Uh, so these are like you can see that once the cable, once the casting is done, and suppose we need to make certain alterations in the beam, in the floor, we can do with that. You can see that in already cast slab, we are doing some other treatments to the post tensioning floor, like that. This is a cutout, maybe like that. Also in some of the portions, like in existing structure, we may employ the cable like this. In case of restriction, we are stressing from one of the sides only, having the cable in this direction, in this particular profile. The cables are in curve shape, and we are stressing from one of the sides only, because here there is no uh, you cannot stress the cable from this end. So these are possible. So this system is very flexible. This cannot be done with other systems like bonded, because they have a flat duct, and that duct cannot be bent in this horizontal direction. You can see the other views. You can see the cables are being laid in this direction, and these are actually stressed from this. So it is very flexible system. You can see some of the images. Here also you can see that the face is not orthogonal to the cable. It has an inclined face. So again, the cable force is in this direction, right? So you can see that there is a mechanism to take care of this inclination by this system. Now extending a PT beam, you have already a PT beam, and now if you want to extend that PT beam, these are the PT beams. And in this project, this is a project of Hiranandan in Mumbai. They wanted to extend the PT beam after construction, after having it all done. So we make them to extend the cables by providing the coupler. You can see that coupler. These are the old cables. These are the old cables. These are the new cables, and it is joined by this coupler, and then we can move forward for the extension of the beam. Trimming of PT beam. PT beam can be trimmed once the PT beam is done. In this geometry, these are the PT beams. You can say there is a cantilever on both the sides, and the cables are actually anchored in this space. Now client wanted to trim this boundary of building from this face to this face, right? It was around 200 mm, 8 inches, 500 mm, sorry. They wanted to trim this 500 mm because of municipal requirements. And once it is done, it was to be executed now. So we trimmed this uh, beams. You can see the anchorages. These are the anchorages before. And now those were to be brought to this level, right? So this was the original dimension. Now it has brought to this, and then uh, we make them to work out, and it was materialized. Now cut out in the PT slab. You can see small cutouts. This is not actually the cutouts, but core cuts. You can say core diameter maybe around 3 inches, 2 inches, 3 inches, 4 inches diameter core to take out the sleeves, or to take out the services. You can see in existing PT building, you can see the same diagram with the laying of the cable, and you can see the marking of the cable, and these are the cutouts. Same way in these are the cutouts, irregular cutouts. Locations are irregular, but still we were managed to get through these cutouts in existing PT buildings in our projects. Then small cutouts like 2 feet by 2 feet cutouts. This can be easily materialized on site, but with our permission, we get back with the design part and we check the with and without this cutout, what is the design part, and then we can approve this. Maybe we can shift little bit here and there the location of the cutout, and we can permit, and then it can be materialized on site. Large cutout, maybe the cutout of size of 40 feet by 10 feet. This could be the size of cutout, and in that case, this is a large size cutout. 40 feet is not a small dimension, and it is in PT slab. So this face, you can see this is all cutout. So this was existing slab. Now it is cut. The concrete is removed, and these are nothing but the cables. So cables are actually managed like this, and then this was a cutout. Slightly more than the cutout is removed. The concrete is removed slightly more than the cutout part, and now this face is treated. This is the face of cutout. So the cables are being again anchored with the new anchorages, and cable are taken out like this. Then we also mark the cable. The status of the cable is good. Actually, still the part the you can say the grease is green enough, or you can say grease is yellow, and still it is having a good amount of lubrication after an year or so, because this decision was after construction. After an year, they wanted to have this cutout. So this is a phase one, wherein we remove the concrete. This is phase one. This is a phase two, wherein we set up the end conditions, and let us go to the phase three. So this is a phase three, wherein this part is cast. You can see that part is cast, and then we stress from this end. This is the size of cutout, you can say. Now on this part, structurally there was a need of a PT beam, so we introduced a PT beam here because there was nothing to tie this part of the beam slab. So there was a PT beam in existing structure. Demolishing of PT slab panel due to certain bylaws, local municipal constraint. Client wanted to demolish the terrace, or you can say the roof of the PT slab at the roof. So and it was materialized like this. You can see demolition of PT floors. Now this is the building plan. It is a huge mall structure having maybe more than this may be more than 100 feet. This may be more than 50 feet, like that dimensions, and uh, uh, this may be more than 100 feet, and this may be more than 200 feet. Client wanted to remove this portion. This portion is to be removed. All the floors, maybe 6-7 story building, and he wanted to have a different scheme in this portion, and he wanted to have this part intact. This part is to be kept as intact in Surat. So we suggested them that this portion is to be demolished. Okay, then these are the points to be treated before it is demolished. So these are the separation points. So we treated them, and once it is treated, then the remaining part is demolished, and then there was a new scheme in this portion. Let's see the photographs. These are the photographs from the Google. You can see that this was a project. There is a bridge, there are cutouts, and this is a project. Client actually bought this land afterwards, after construction of this building, and now he has changed his mind, and now he wanted to demolish this portion. So he demolished this portion. It was all PT, and then now the new scheme is there, right? So again, in new scheme, he we were there to construction of certain curve-shaped beams and all these things. So let's see the photographs. So this is the interior while demolition. You can see the bridge, main middle bridge part. You can see some of the PT members are being already demolished. You can see terrace part. You can see here, it is under demolition. You can see the debris and some members. This is the connection point. You can see here the connection point is being demolished with the proper care. These are under demolition. Again, here also you can see the another angle of the demolition. Here also it is demolished, the connection part. We watched out the condition of the cable because it was around maybe more than 2-3 years of construction, and now this phase has come. So we try to review the condition of the cable, but after this 3 years, 3 or more than 3 years, still the grease is proper without any aging effect, and it was good actually that it has served its purpose. The condition of the cable still it is good. Retrofitting and re-strengthening with the external PT. You can see that this floor is a PEB floor, and it has deflected. Like this is a bottom line. You can see that the bottom line, and here you can see that this portion is having a deflection. You can see the red line. If you follow the red line, you will be able to mark up the deflection point. So that deflection point is nothing but it is a mid-span portion where it deflected. So we treat them not to deflect much by having this blue color cable. Those are provided externally to this beam, PEB beam, steel beam, and then it was ensured that the further deflection will not be there, because there is a R&D center about this, and there were all these laboratory equipments were there, and they were sensitive to the deflection, further deflection, so they wanted to control over the deflection afterwards. A few iconic projects constructed using this technology are like this is a Urmi Estate building, a 40-story building, wherein PT is unbonded PT system has been employed. It is completed in 2012. This was one of the top 10 building in India in those days, in 2009 to 2012. It was one of the top 10 building as far as height is concerned in Mumbai and in India. This is another building for TCS, Tata Consultancy Services. This is a phase 1 building in Mumbai, constructed by Hiranandani Group, one of the renowned developers in the Mumbai. And we recently completed this phase 1. Phase 2 is also completed by now, and phase 3 is on progress right now. So all this phase 1, 2, 3 in PT building with flat slab skin. This is a IT park wherein there is a podium. 1, 2, 3, 4 floor is a podium slab where parking is there, and above that there is a office building, IT park. You can see the construction is going on with a flat slab skin. Sorry, it's in Mumbai. It's in Kansoli side. This is again a commercial complex for one of the leading developer in Ahmedabad, Shivalik Group. This is a Shivalik Ship project nearby ISKCON circle in Ahmedabad. You can see some of the inclined columns and it's having a floor plate PT. This is an institutional building for Sandeep Foundation campus. It's completed in 2013. There are large span classrooms, library block, admin block, large span, heavy load. This was done by us with unbonded PT system. This is one of the corporate buildings in Baroda, and it's K10, and you can see the iconic shape of the building. Here the floors are of PT. This is also an iconic building, Cloud 9. It's a high-end flat skin in Vadodara. You can see the curvature shape and facade. It's a flat scheme. There is no beam inside. It's all slab, shear walls, and columns. This is a project of Linde. Right now, the new building of Linde Engineering in Baroda. It's nearby Nilambar Circle in Vasna Bailey Road. It's done in PT, unbonded PT. The special part was this. This part is also underground. There are underground floors, parking floors below this, and this is having a huge load of soil and this soil treatment and ground treatment, and it has undulations up and down, and it is done in PT. Let's work on the rumors that you may hear or you may heard about the PT system, especially for unbonded PT system, that you cannot drill or make openings in PT slab. But right now, we have discussed, and it's mostly possible using proper procedure. Only thing is, you need to make out the proper procedure. Second one is, if you drill into a tendon, it will fly out of the building. We never have experienced such kind of event. It cannot be completely flied out from the building in any case. Third is, it is impossible to upgrade or repair a PT structure. We saw some of the slides that there are ways to upgrade and repair the PT structure. It should be well defined. There has to be a well defined methodology. With that methodology, we can do those things. PT structures are not durable. Of course, PT structures are more durable. You have a better control over the tensile stresses, cracks, and hence you can achieve more durability with the help of PT. It is expensive than the conventional structure. It is not expensive, but uh, overall scenario, it will turn out to be economical and durable. So with this, thank you all, and let me conclude. And if you have any questions, I'm looking forward for the questions.
Sir, can you stop your screen sharing?
Yeah, let me go through that.
Sir, my screen is visible to you.
No, not yet.
Yes, Ankit is visible.
Okay, sir. Sir, it was a really nice and informative session. I think all the aspects were covered in this session. Still, we have some questions. So the first question is, which system of prestressing is widely used in India?
Uh, Actually, to be more specifically, pre-stressing has a pre-tensioning and post-tensioning. To be more specifically, in post-tensioning, right now we are into Indian market since 2006. Before that, the bonded post-tensioning system has been there in India in building sector as well. It is mostly used for bridges, but it is also used in building sector. And now, since 2006, we have completed more than 1,700 projects till now. So now you can say that now people are accepting this technology, new technology, and uh, they are taking benefit of this. We have completed like around 1,700 projects till now. So you can say that now it is you can say a prevailing system in building technology in building systems.
Sir, another next question is, how many types of splicing arrangement are
Have
widely
you shared?
used in?
Let me interrupt you. Have you shared your screen?
Yes, sir.
I am not able to see your screen.
Rakesh, sir, is it visible?
Yes, it's visible.
To me.
Uh, Sir, no
Yes,
problem.
now
I'll ask the
now it's
question.
visible. Now it's visible.
Okay,
Yeah,
okay, sir.
yeah.
So, next
Which
question
how
is,
many
how many types of splicing arrangements are widely used in post-tensioning system?
splicing arrangement is a very special uh, thing actually. No, it is not a routine practice, but in special case, splicing can be done. And we did couple of projects, maybe 4 or 5 projects with this, where splicing arrangement has been utilized, but it's not you can say very typical. It's a non-typical item, and it is a special case wherein we need to use that. But this splicing arrangement is you can say it's a common system that is aligned. You can say it's like a but system, right? It's
Okay,
like a but, or you can say it's like a wedge and wedge kind of arrangement is there. So with wedge action, splicing is achieved. What are adaptive techniques to reduce the stress at end zone? See, stress at end zones are about to be there. Uh, you need to make sure that you have enough confinement at the end zone to take care of those stresses actually. So if you are coming across the stresses, actually what happens is, in case of monostrand system like us, we have a monostrand system, and in case of monostrand systems, these stresses are quite reduced at end zones, because each cable has its own anchor plate, and that anchor plate is and the size of anchor plate is such that you know these stresses are minimized. But in case of multi-strands, like in case of bonded, there are maybe 4 or 5 cables together, and it has one single anchorage. So in that case, you may come across stress concentrations or high stress zones at the ends. Well, when your anchorages are there, and in that case also, you can design those things accordingly, whether it is a high stress zone or less stress zone. You can design accordingly and provide the confinement still, and you can manage uh, your forces accordingly. Which software used to design pre-stress system? There are a couple of softwares. Even you can design with your hand calculation as well. And there are a couple of softwares, like there is a software called Adapt. There is a software called Bentley's RAM concept. There are softwares like uh, you can say Safe. Safe is also there. CSI, which has a capability of analyzing of PT flows. Now in ETAB also, they have a feature of introducing PT forces and PT cables in the ETAB. Also, I think it is also there in STAD. It is also there in STAT 2000. So there are a couple of softwares with which you can design the pre-stress system. Does it requires any maintenance after installation? I would say no. It doesn't require any maintenance after installation if it is properly handled. Right? If everything is properly handled based on the design requirement, it doesn't really need any maintenance afterwards. How to do rebarring anchor fixing in PT slab? See, the way you are doing in the normal RCC, the same way you can do with the rebarring and anchor fixing. Only thing is you need to make sure that you are not about to damage any PT cable. So once you have ensured that you are not damaging PT cable, you can do the way you are doing with the conventional uh, structural system. It's the same.
Okay,
So
sir. Actually, one more question from my side.
hmm,
Nowadays, most of the builders are using PT slab, means PT technique, and
right.
I have seen some cases. In that case, they are not able to achieve the minimum strength criteria from concrete. So, how we can means how to deal with these kind of cases?
See, in 2006 when we entered, uh, you think I think you should take this in positive way. Uh, so before this, what was the scenario of concrete when it is RC, right? When it is RC structure, and if the concrete is not good enough, if it is not serving the design requirement with which the design has been carried out, suppose the design is carried out with M30 concrete, and on site, if the concrete is not even M15 or M10, what will happen to the structure? And as you know, the site conditions, there are very rare cases where they measure the cube strength, right? So this was a case before 2006 when we entered in the market. Then we started asking for the cube strength results. So now client has to perform the cube strength report and they have to submit to us. Then they start realizing that the concrete may or may not be having enough strength. So is it good that the concrete, real concrete, is not having strength, but we are under impression that it is having strength? So it is a bad news for us, right? Bad situation for us. So it's better to have a realization of the material. So it started after having this, after introducing the pre-stressing force. So the secondly, when we apply stress to the cable, what happens is the cable is stressed to its 80% of the strength, right? So cable is also stressed. Cable is also tested to its 80% force. So cable is ensured that it has a good material characteristics and it handles that force. So we can ensure about the cable. Secondly, in other way, we are ensured about the material of concrete, that it is also good, that it holds the force, so it is also good. Now, not only the material of concrete, but the way it is placed in the member, right? If there is honeycomb, the concrete is of good quality, but the way it is placed is not good, then there could be honeycomb in the concrete. Just think of a column beam junction in RCC case, wherein you have a vertical reinforcement of column, main reinforcement. There are stirrups of column. There are a beam running in one direction. There are beam running in the other direction. So all six directions are occupied with the reinforcement, right? There are stirrups, and the reinforcement is huge at the top part of the beam, then the bottom part, and you are casting from the top part of the beam. right? Now, what happens to the casting part and the status of the casting in case of you have a congestion of the top reinforcement from both the sides of the beam and as well as in column? What happens to the casting part in that column beam junction? Right? So if your concrete is good enough, but if it is not poured in proper way, the compaction is not achieved, there could be a problem, but we are not able to realize that problem right now. There could be honeycomb in the column beam junction, but there is no way to identify that, no way to ensure that there is nothing inside, right? So what happens in that case? So there are certain limitations, certain you can say certain limitations we are living with. Similarly, here there is a beauty that if concrete is not good enough, it will show you the sign, and before it is under service condition, you can treat that, and that is the beauty of having a, a live force or active force design, right? So we are considering in other way, and this is an advantage that we are knowing, or we came to know the status of concrete, the status of steel before it is under use, right? So we think we see the event with that perspective. So it is better for us that we came to know about this kind of events of failure of concrete, right, while stressing. We came couple of we came like maybe mostly in 2006 this was the challenging part for us, but now client as well as the RMC supplier, they have learned a lot, and now they are providing a good quality concrete, the good placement of the concrete, and that is how the structure is benefited by this awareness. I
Okay,
hope
sir.
I have given you the answer
Yes,
of the
yes, sir.
questions indirectly,
Yes, sir.
right?
Yes, sir. So now, sir, we don't have more questions.
Good.
So, sir, can we end this session?
Yes, please.
So, sir, so on behalf of M.S.Patel Department of Civil Engineering, CHARUSAT, we are thanking you to deliver this informative lecture. And personally, I feel that we have learned lots of things about pre-stress concrete. So it was really nice session. We are getting very positive comments from participants. So I think all participants are having enjoying these sessions. Enjoyed this session. So it was really nice session, sir.
Thank you, Ankit. Thank you, Bhargav. Thank you, P. Mahendra, and all. Thank you, all listeners. Thank you for having your time and sharing your time with us. So,
Okay. So we can
yeah,
now end this session, sir. Thank you,
yes,
sir.
please. Yes. Thank you. Thank you all.